Good afternoon, everyone. Lunch is all out of the way now, I guess, so anyone falling asleep yet from the food? If I do, just throw something in this general direction, I'll wake up again. So my name's Dave Page, as Chris said. I've been working on PostgreSQL since about '97. One of the core team members, lead developer on PGAdmin, also work on the web and sysadmin teams, and as a board member for Postgres Europe and the Postgres Community Association of Canada. For my day job, I work for EDB. I'm responsible there for our tools, cloud products, configuration management, packaging and distribution, and infrastructure. Kind of a jack of all trades, really. But anyway, today it's cloud I'm going to be talking about, specifically OpenStack, and just some general information, tricks, and things that are useful to know when you're running Postgres on an OpenStack infrastructure. So what is OpenStack? Anyone used it? Familiar with it? One person, two person, three, four, five. All right, so OpenStack is a cloud environment. It's designed to be fairly similar to Amazon's AWS. Companies using it for private implementations, but also for very large-scale public implementations. Obviously, examples of those are Rackspace Cloud and HP's Cloud, which are both based on OpenStack. Rackspace, in particular, are one of the major contributors to OpenStack. It's got a modular design. There's lots of different components that you can plug into it depending on what you want in your environment. Some of the ones we'll be talking about today are the image service, called Glance, the block storage service called Cinder, compute service called Nova, networking service, which in modern releases is a new module called Neutron. Previous releases had the networking was built into Nova, which was not nearly as flexible as the new Neutron code. And finally, the object storage service, which is called Swift. So I'm going to run through these very, very quickly, just give you a bit of background on what each of these services are, and then we'll look at how each of them can be used with Postgres in a cloud environment. So the Glance image service. This is basically the storage system in which you're going to store images of your virtual machines, as well as snapshots of the virtual machines. You can obviously pre-configure images or snapshots, get the right operating system and software on them for whatever you want to do, and share those images with whatever projects you want. You might hear me mention projects or tenants later on in the talk. For some reason, OpenStack have a bit of an internal argument about whether different groups of users should be called projects or tenants, so they seem to use the two terms interchangeably, which is both annoying and frustrating sometimes. So, in a nutshell, the image service is where your blank virtual machines live. The Cinder block storage service is basically analogous to Amazon's EBS service. I'm sure probably far more people in the room have used Amazon in the past, and you've probably all come across EBS. Provides block storage devices to virtual instances, so you can provision a Cinder block device to a virtual machine and then just mount it as if it was a drive. These can be provided from one or more service nodes via a controller node. So the service nodes are the machines that are actually providing the storage. They can be all sorts of different technologies, just a simple machine running LVM, GlusterFS, NFS servers, various different types of SAN, and so on. Then controlling all of that and directing requests for storage devices to the right type of storage, you've got this controller node that sits in front of all of them. The Nova Compute service is really core to everything. You can't do anything particularly useful with OpenStack without Nova. Basically the equivalent to Amazon's EC2. And its primary task is to schedule and run virtual machine instances on hypervisor machines or compute nodes. Nova allows you to specify multiple different machine flavors, so you can have in Amazon terms, say an M1 small, which has, I don't know, I forget the exact specification, but maybe a couple of gigs of RAM, 2 virtual CPUs, and a 20 gig root disk. Or you could have much larger machines configured exactly as you want. The compute node selection is actually very configurable in OpenStack. We have pluggable scheduler filters that help us define where instances are going to actually run when they're launched. You can target images to specific hosts. So one of the things we do at EDB, for example, our QA team use OpenStack to do a lot of their testing. They can fire up instances very, very quickly. When we're using SUSE Linux, for example, we have to buy licenses per physical machine. So we target the SUSE instant images to a specific group of hosts, so they can never run on more physical machines than we've got licenses for. You can target machine flavors to specific hosts, which is also useful. So you can have a machine flavor which is a high memory flavor, so you've configured one with 64 gigs of RAM, and you can make sure that that particular machine flavor only runs on a particular set of machines. And you can target instances to hosts with free resources. That's fairly fundamental. You need to make sure that you're going to launch an instance on a machine that actually has the resources available to run it successfully. Obviously, you need a network to talk to the rest of the world and provide communications between the different virtual machines, and that's where the Neutron service comes in. This provides network interfaces and network interconnects between the virtual machine instances and allows those instances to connect to one or more virtual networks. You can map floating or public IP addresses into a virtual machine. So these are IP addresses that sit outside of the OpenStack environment effectively on your own internal network. Amazon calls them elastic IPs. And you just map them onto an interface within the OpenStack system. You can also configure firewall rules for ingress and egress, which allow you to fairly tightly lock down instances to only allow the traffic in or out that you're expecting. Next up, we have the Swift object storage. This is basically the same as Amazon S3. It allows you to store whole files with HTTP GET and PUT requests. It's very, very highly redundant. You have lots of servers running in a Swift system, potentially, each one with individual disks. You don't run RAID on each of the servers. You just run individual disks on each server, and Swift itself will distribute the objects around a group of servers so that you've got whatever redundancy requirements you have. Once it's set up, it's pretty much seamless. If you lose a drive, you can replace them and it'll just repopulate everything. If you lose an entire server, you can replace it and Swift will just repopulate it. Very, very difficult to break, which is kind of handy in some situations. Now, there's one other service that I didn't mention earlier. Anyone heard of Trave? Okay. So Trave is, I guess, OpenStack's answer to Amazon RDS. Now, I'm not going to talk about it today other than this slide, just to explain why I'm not going to talk about it. It's still in the relatively early stages of development. It's basically a first-class component of OpenStack, but it's still very, very basic in what it does. It's mostly focused around MySQL and Cassandra at the moment, although it is being designed to work ideally with pretty much any database system. However, it doesn't have support for any kind of clustering, replication, or any kind of non-trivial setup. Basically, it's just a way of launching a virtual machine that happens to have a database running on it. The API that's being developed by the OpenStack guys for Trove also seems to favor database operations, the sort of things you do in pSQL or in pgadmin. So create a database, create a role, those sort of operations. They haven't developed the API yet to allow for things like building clusters. They haven't even put in stubs for the APIs for those, whereas they have for some of the other things. So at the moment, my opinion really is that Trove is is not what most of us probably need in a database service in something like OpenStack. You know, we need to be able to launch a database, but we can do that trivially anyway. And we can create those tables and those roles using pgadmin. What we really want moving forward is the ability to have a scalable cluster with scalable storage and so on and so forth. And that doesn't seem to be the direction Trave's going in right now. So, while I grab a drink. We've got all these different modules in OpenStack, but what can we actually do with them? Well, the first thing is we can manage our database server images. So we can pre-configure a standard database image. So if you know that you want Postgres to always be set up in a certain way, which, believe me, if you're managing a lot of Postgres instances, you almost certainly do, then we can pre-configure an image that has Postgres set up exactly as we want it. So every time we deploy a new instance, it's there, it's running, we know exactly where the software is installed, we know exactly how it's configured, and it's going to work the way we expect. That's consistent. And consistency is obviously one of the key things you need when you're managing large numbers of servers, because it makes it much, much easier. The other thing it allows us to do is to pre-install commonly required software, things like procedural languages. If you know you're always going to use PL Python, you can pre-install it so it's there, ready and waiting in the template one database. You can pre-install WALE if you want to do WAL archiving. Things like PG Bouncer, PG Pool, PostGIS, all of those things can be ready. So you've just got a two-click launch or whatever it is, and everything you need is ready to run. In addition to the consistency, of course, this minimizes our launch and deployment time. It makes it very, very fast. You want to play with an instance just to test something, click, click, 2 minutes later it's there, it's running, you can do what you want with it. Now, I mentioned earlier that the image service also stores the snapshots, and you really have kind of two options when you create your database image. What you can do is create an image with just, say, rel 6 on it, install Postgres, set it up as you want, and then you could snapshot it, and then you could launch instances from that snapshot. Or you could create a whole new image. There's not much difference between images and snapshots, technically. I'm kind of OCD about these things, and I tend to think as snapshots as more of a backup, and images as kind of my blank template, which is, and I don't really like mixing them up, but that's just me. One of the nice things about images is you can consider them to be sort of the blessed and approved standard things, where it's quite easy to get lost in a sea of snapshots if you're doing backups with them all the time. And they are pretty handy for doing backups, so don't not use snapshots. But the other important thing about them is that images are clean configurations. So whilst you may have taken a snapshot of an instance that you've got set up just as you want it, it's going to have things like log files in it, it's going to have shell history, and all sorts of other just artifacts of the fact that it's a machine that's been running before. When you create an image, one of the things you're going to do is clean it up first, which gets rid of all those things and gives you a nice clean machine to start from. So it's actually pretty easy to create an image. I'll just run through a very, very quick example here. So the first thing you do is create a small root disk in qcal2 format, which is a one-line command in Linux. You normally want something fairly small because you want it to be able to run in the smaller machine flavors. And the root file system can be automatically expanded when it's launched. So if you run it on a machine type that's got a larger disk than your initial image, then it will automatically resize the file system on launch. So create your qcal2 format disk, and then personally I use KVM on RHEL with the virtual machine manager in Windows there, GNOME Windows. And I use usually CentOS on there, because typically we don't use RHEL in our cloud environment just for licensing reasons. Install any required software on it. I always then add the epool yum repo. If you're using Debian or something, there will be an equivalent. I'm not that familiar with Debian, so I couldn't tell you what it is. And then at that point, we install the cloud init package. So this is a bit of software that will run when the instance is first launched. And what it's going to do is the resizing of the root file system that I just mentioned. It's going to grab the SSH keys that you've configured as a user of OpenStack and inject them into the image or into the instance so that you can actually log in and do various other initialization tasks. Couple of one last thing, we disable zero comp for the network. It just makes it actually work properly. Shut down the VM, and then we run virt sys prep from the host machine that we've created the instance on. And what that's going to go through that step that I mentioned, the cleanup routines, just to get rid of the log files, the bash history, and all those sort of things. Once we've done that, we've got our image. It's basically that qcow2 file. So we can upload it from the command line using the glance command line interface. Very, very simple. I'm just going to run the command there. It's going to tell it, create an image. The name is Postgres 9.4. The disk format's qcow2. Container format's bare. It's public, so everyone can see it. And show me the progress bar while you're doing it. And then feed it the image. And you'll get some output back out of glance like that, which gives you things like the image ID, various other properties. And that's it. That's your standard image for Postgres 9.4 created. Any questions? Carry on. So, database server machine configurations. And this is where I get very confused because PowerPoint started blanking out the next slide and it looks like it's all got corrupted. But thankfully, no, it hasn't. Okay. So on Amazon, you have different machine instance types, M1 small, M1 XXX large, and various different configurations of memory, CPU, root disk, ephemeral disk, and so on. In OpenStack, these are the flavors. I'm British, so I always put the U in flavors. OpenStack doesn't, which I always have to remember whenever I type a command. Here, what they describe is the number of virtual CPUs that are going to be allocated to that instance, the amount of memory, the amount of root disk, the amount of ephemeral disk, and swap space, as well as any other attributes that we care to assign to that database flavor. The additional attributes allow us to do matching later on when we run the scheduler that actually launches the instance. For example, we can put an attribute on there that says this machine type needs to run on a node that's got SSDs on it for its storage. Now, once we've got a machine type, we need to make sure that our databases actually use it and that it runs on the right type of machine. So what we can do is target that machine flavor to a specific host aggregate, which is basically a group of compute nodes that we've arbitrarily put together. So in our case, it might be a group of all the machines with SSDs. Now the way we do this is we create the host aggregate or group containing the desired nodes. We add the property to the host aggregate to identify the attribute that we're going to use for matching. Then we create the database or the machine flavors that we want to run our databases in. Then we add a property to that flavor that corresponds to the property we added on the host aggregate, and then we can share the flavor with our users. And then what happens is when you run any machine or you launch any instance that uses that machine flavor, it's going to get matched to one of the compute nodes that is a member of the host aggregate. So you know that your database machine type is always going to be executed on a machine that's got SSDs, no matter what other machines you've got in your cluster. So we'll go through a very quick example of how to do this here, using the Nova command line tool this time. So we aggregate create PG servers, which is just going to create the empty aggregate. What I then do is add a machine called nova5.ox.uk to that, which is my one that I want to run all my database servers on. And then I set the metadata, the flag that we're going to use for the matching. And in this case, we're creating a flag called PGSVR and just setting it to a value of true. We'll then create the flavor that we want to use. So in this case, as you can see, ephemeral disk size of 0, swap space of 4 gigabytes. We're going to make it public. We're calling it pgserver.small. Auto is just a flag to generate the ID. You can give it a numeric ID if you prefer, or it will just create one of these UUID style values. 4096 is the amount of memory in megabytes, 40 gigabytes for the root disk, and 4 virtual CPUs. So that creates the basic flavor, but at this point it doesn't have the attribute needed to match it into the host aggregate. So what we do, and hopefully you can see that, it's kind of small on my screen. So we're just going to set using the flavor key option to the Nova command on PG server small aggregate instance extra specs PG server equals true. And that doesn't return anything, so I've just told it to describe the flavor to me there so you can see the results. And this has added basically that extra specs line. Now, what's going to happen then, as I say, that will match that to the host aggregate and ensure that the machine runs, your database runs on the machines that you've spec'd out for running databases. So while we're here, I mentioned scheduler filters a number of times, but I haven't really explained what they are. When you launch an instance in OpenStack, what it does is it calls this thing called the scheduler. And the job of the scheduler is to find a host to run the instance on. It has a number of filters in there that you can configure which filters are used. And the job of each filter is to reject hosts from a set. So initially, all the hosts that you've got will be passed into the scheduler, and each of the filters in turn will reject 1 or more or 0 or more different hosts until you eventually come up with a host that the instance is actually going to run on. So we have filters that can reject based on things like capability, the current utilization of the machine, so whether it's already maxed out on CPUs or disk or something, the physical location. You might have users that need their machines to be in a specific physical location. Affinity, certain machine types, you may want to say, well, once this machine starts running databases, I don't want it running anything other than databases. So you can set up affinity between the machine flavors and arbitrary hosts. Also things like tenant isolation. If you're providing services for a group of companies, for example, one of those group companies may have data security requirements they've got to meet. For example, they're processing medical data. So you can set up tenant isolation so that specific tenants will only run on specific compute nodes. So the scheduler goes through, it filters out all the different nodes, and eventually it will come back with a list of 1, or if you're unlucky, 0. Sometimes 3, 4, 5, 6, in which case we have a filter on the very end which will just pick one at random. Now, the example we just gave there used the aggregate instance extra specs filter, which is quite a mouthful. But you can also write filters in JSON. There's a JSON filter that allows you to define them. Or you can write them from scratch in Python. The code is actually pretty simple. You can just use one of the existing filters as an example, copy and paste it, and rework it as you need to. Okay, any questions on that before we move on? So either I'm doing really well and explaining everything nicely, or it's just a really boring talk and you're all wishing I'd go away and go back to England. I'm hoping it's the former. We'll see. You're collecting feedback, right, Chris? Yeah. Well, that might determine whether I come back next year then. All right, instance storage. Where do my VMs live? So there are a number of places when you run your virtual machines on the compute nodes, there are a number of places where those virtual machines can actually live. Originally when Amazon was launched, all machines were ephemeral. And that was because they all lived on the what was known as the instance store. Now the way this works is when you launch a machine, the scheduler then picks what host it's going to run it on, and the image that you're launching is copied out of Glance and onto that hypervisor. Now, at Amazon scale, what that effectively means is if you try and shut down an instance and then restart it, it could end up on some completely different node 1,000 racks away, and yeah, they just made everything ephemeral at that point because trying to copy things around as you started and stop them was just not really going to be practical. Now, when you set up OpenStack for the first time, that's typically how you will run things. It's how we run things. We use the instance store on our cluster in EDB, which is not huge. We've got 11 compute nodes on there at the moment. Effectively what this means, the machines are running on the local disk of the compute node. Now it's easy to set up, it's pretty performant, you know, it's all local I/O, and it needs minimal hardware. Downside of it is it's a pain in the ass to move instances from one machine to another. If you need to take a compute node down for an extended period and you need to move an instance to another box, that can be difficult. It's also potentially less reliable because if you've got a bunch of compute nodes just with a couple of drives in each of them, potentially you've got a higher chance of those failing than you would have on a higher end storage system. In fact, you almost certainly have a higher chance of them failing. Now, one of the ways you can get around that is to use shared instance storage. So this is also pretty simple to set up. The idea is basically what you're going to do is use that directory that the instances would have been stored in the local scenario, but you're going to make it an NFS mount onto a remote file system or an iSCSI target or whatever. Then you actually share that storage between all of your compute nodes. Now that allows for a really easy migration of instances between the different nodes. So if your database server needs to be migrated because you've got to do some hardware work, you really only need to shut it down and bring it up on the other node. You don't have to copy anything around or anything like that. Obviously, you've got the other advantage that it can be a lot more reliable. If you're using a SAN, then you've got lots of redundancy and so on. It's clearly going to be more reliable than just a pair of SCSI drives. Downside is that what, from the instance's point of view, is local I/O is actually over the network. Now, you know, that could be fiber channel, it could be 10 gig Ethernet or whatever, but as you scale up, that's potentially going to get a lot slower, or it's going to get a hell of a lot more expensive. Probably a lot more expensive. So you get more flexibility, but when you get into the larger scenarios, it's going to, you know, talking big, expensive storage systems to deal with that. As a result of that, it's also more complex to set up and maintain. Now, the third option is volume storage. If you've ever launched an instance in Amazon AWS, one of the options you get is an EBS-backed volume. And what that basically means is that the root file system for the instance is actually in an EBS block device. In this case, the root volume will be stored in your Cinder server. Now, the nice thing about this is it's available as a launch time option as long as you've got Cinder installed. So in our setup at EDB, whenever I launch an instance, I can choose whether I'm using the local instance store or if it's something I know I'm going to need to move at one point in time or likely to need to move, I can choose right then to store it in Cinder instead. You've got easy migration of instances, exactly the same as if you're using shared storage. And again, it's potentially more reliable because for Cinder, you're probably using a much higher end storage system than just your couple of SCSI drives. Downside again, the local I/O is effectively over the network, more complex to set up and maintain, and it can be far more expensive because you're using that much more high-end gear. So I haven't really spoken much about Postgres on this particular set of slides. But what I've tried to do is describe some of the pros and cons, and you need to then apply those to your uses of Postgres and make a choice as to how you're actually going to set this up in your environment. If you want, you know, something that's reasonably performant, cheap and easy to set up, then go with the local storage. If you absolutely know you're going to need to move things, then choose one of the other options. It really comes down to how you're going to use Postgres in this environment. If you're just tearing up and down test machines, then it probably doesn't matter. You can use local instance storage. But if you're going to be running things on the long term, you probably need to think about the fact that you might have to move things from one compute node to another in the future, so shared storage becomes a lot more attractive. Okay, so that's the actual instances themselves. The other side of that is, where do we put our data? Well, the easy option is just stuff it in the instance. If you're just running a small database, then why not just bung it in the root file system? You've got plenty of space there. You can have 100 gig flavor, and for many applications, that's perfectly fine. One of the things we can do if we run into problems there is we can actually resize the instance. So if you start running out of space, you can resize that virtual machine instance up to a different flavor, which will give it more disk space. Downside of that is it will pause the instance while it's going to do it. And it's not particularly elastic. It's, you've got to go and do some maintenance work. You've got to pause the instance, run some commands in Nova to resize it and change the machine flavor, and then it comes back up again later. Another downside is that you get slower snapshots. If you're snapshotting and you're using the root volume, it's going to actually copy those snapshots back into the glance image service, which can be kind of a pain. If you need to do some maintenance very quickly, you want to take a snapshot back up, you might not want to wait for a 40, 100, 200 gig snapshot to get copied back across. The other option we've got is actually to store the data in Cinder in the block store. Now this is a little bit more complex to set up. What you're basically going to do is fire up your instance, provision some Cinder storage, and then mount those block devices. Now it's more expensive for a high performance setup for all the reasons I mentioned earlier. But the nice thing about it is that you can add storage on the fly, because you can add additional volumes and use LVM, for example, to extend the file system across those volumes. So you can do that with no downtime at all. And that's actually really handy. If you've seen the Postgres Plus Cloud Database product that EDB produces, that's how we deal with elastic storage in the back end. The system will dynamically add additional EBS volumes and then extend the file system across those. You don't really know it's happening at all until you get an email saying, we've resized your volumes because you were running out of space. And that can be really handy. It saves a lot of messing around. The other nice thing about Cinder is that I mentioned right at the beginning of the talk that you have lots of different storage service providers, effectively, that sit behind this controller. What this allows you to do is actually have, in a similar way to the machine flavors, you can have different storage flavors. So you can specify that I've got a storage flavor that's all SSD, or a storage flavor that's very high speed, 15,000 RPM, SCSI drives, or just some very cheap but large and slow drives as a third type. So you can select that when you actually create the volumes, which allows you more flexibility to target those database servers and those data directories onto the most appropriate storage for what you're trying to do. The other nice thing about Cinder is it can do really fast snapshots. Our Cinder server is just a very, very simple file system one. It provisions LVM logical volumes and then attaches using iSCSI to those. You can use SANs, whatever technology you want. There's a bunch of different options there. But when you're doing LVM snapshots or when you're doing a SAN snapshot, obviously it's very, very fast compared to copying a snapshot back to the glance server across the network. Any questions at this point? Still none? Wow. Okay, I'm beginning to get worried now. All right, let's look a little bit at the networking side of things, firewalling, first of all. So the Neutron service provides things called security groups to define firewall rules. By default, there's no ingress access allowed to anything. Each security group can define one or more ingress or egress rules. They can be IPv4, IPv6, ICMP, whatever you need, really. And each instance that you create can have multiple security groups associated with them. So you can create one security group that will allow SSH in for administration, another one that opens up port 5432 that you can use on all your database servers, maybe another one that opens up 6543 for PG Bouncer, and then just apply those groups to whichever nodes are appropriate for what you're doing. This makes it nice and easy just to have a standard set of firewall rules for all of your database servers. You can just apply the same thing over and over again. If you want to change it, for example, you decide, well, I'm actually going to run PG Bouncer on all those servers and have some complex clustering set up where it tries to fail over and load balance between other ones. Well, you can do that easily. You can just open up that additional port for all of the servers in one foul swoop. Now, I didn't mention before another module OpenStack provides, which is called Horizon, which is the dashboard system. Horizon's pretty good just for setting things up and running in sort of day-to-day operations. It's not great for doing things like creating machine flavors. It doesn't tend to deal with the low-level operations that the administrators do quite so well. But as an end user, it's quite usable. In this case, what you can see here is the security group rules for a group called PG Server that I've set up, where we're just allowing ingress for IPv4 on port 5432. Port 22 SSH is there as well, just to allow us to actually manage those nodes, log in, fix problems, that kind of thing. And we allow egress pretty much to anywhere and ingress of ICMP, so we can ping it and test when things go horribly wrong. Yes? Yes. Yeah, so there's a set of Python tools. The command line for OpenStack is all Python modules you can install with pip. And you have the packages called Nova Client, Neutron Client, for pretty much all the different modules. They cover all the operations you're going to need to do. Horizon is a subset of that. So that was firewalling, which is really pretty simple and straightforward. Networking is a little bit more complex. It's actually pretty easy to use, but the networking is, as somebody who is running an OpenStack installation, the networking side is by far the most complex. When it goes wrong, it can be horrible to fix. But as a user, it's pretty straightforward. It allows us to create one or more virtual networks. We can contain clusters of servers within there. We could maybe put an application server, a web server, and a database server in one virtual network, or a replicated cluster of Postgres servers, whatever we wanted. Really up to you how you choose to use it, but it gives you the way of isolating that group of servers together in their own private network very easily. Very similar to Amazon's virtual private cloud, which I think for new users now, they force everybody into. You can attach virtual routers to the network, so you can set up routing between multiple networks or between the rest of the world. And you can have one-on-one networks attached to each instance, so you can have multiple interfaces on them and set up really quite complex topologies that if you were doing at the hardware level, you'd be messing around with VLANs and router configurations for potentially a lot longer than you would be here. You can then use floating IPs, in Amazon term the elastic IPs, to access the instances from the outside world. So if you've got a cluster of Postgres servers in one VPC, you'd maybe map a floating IP into the machine that's running the load balancer across the top of them. And each network finally can have its own DHCP server and custom routes, so you can set things up so the IP addresses are automatically allocated and the routing is automatically set up as you need. Yep.
All these elements function on computers almost completely mirror Amazon's configuration. Which came first?
Amazon came first. Amazon came first, then Eucalyptus tried to mirror that and did a pretty poor job of it, although I've heard it's got a lot better since. And then OpenStack and CloudStack, I think, came around together about the same time. So there's a very simple example of the network configuration for the test network that I set up here. We've got at the bottom there, the general virtual machine network that all our machines live in. So if anyone just launches an arbitrary instance, it will automatically go in the general VM network. And then the dedicated network that I set up just for my cluster of Postgres servers. And Horizon also gives you can't, I really struggled to get a good screenshot of this that would fit on the slide well and actually be visible. But Horizon gives you a way of browsing through and looking at the actual topology of the network. So in the example here, the blue vertical line is our main EDB network. That's our internal network that spans all our offices. And then the orange virtual network there is the Postgres network that I set up for the cluster of servers, the three of which you can see down the right-hand side there. And then a router in the middle between them. Again, virtual. It's all done using the Open vSwitch package. Any questions? No? All right. WAL archiving. I'm guessing I get a decent show of hands here for people that do WAL archiving. Is that all, really? You know one day you might lose data, right?
Look, you can dump this for
Well, there's certainly a use case for those, but you probably want to be WAL archiving as well. Now, I mentioned we have the Swift object storage service, which is kind of similar to Amazon S3 and what it does, and in the way it works from what I know of S3. And that's ideal for us to store WAL segments and backups in, because we can just fire them off at the Swift system, retrieve them later, and we don't really have to care about making sure they're replicated across servers or across sites, and so on. It's very, very convenient. Also highly redundant, and it scales very, very well. You can just keep adding more disks and so on to Swift and scale up into hundreds of terabytes or petabytes even. What's even better is that if anyone's used WALE before, which was written by the guys at Heroku, that was a cue for a show of hands. Yeah, a few of you. So WALE was originally written by the Heroku guys to do their WAL archiving, their backup archiving to Amazon S3 on the Heroku platform. But WALE now supports Swift as well. So we can very easily set this up so that it archives off our backups and our WAL into Swift. Very convenient, allows us to deal with things like pruning and getting rid of old things that we don't need anymore, and deal with the actual creation of the backups and restoration.
Would you use it for log files?
Sorry?
Would you use it for log files also?
What, you mean operational logs? We could do. I don't think WALE will do that for you. Yeah, you could do. I mean, we use our syslog, but I suppose, yeah, I suppose you could do. Installing WALE is, well, it takes you 10 minutes or so the first time you do it. It's not the most straightforward thing to get right, but once you've done it once, it's fairly easy. It's written in Python, so we do pip install WALE. And then you need to edit your postgres.conf file. First of all, you've got to set your WAL level to archive, so you've actually got some WAL to archive, and switch on archiving, obviously. And then what I'm doing here is I'm actually creating a script called wale.sh, which I'm going to use as the archive command, and just the %p, Postgres will insert there the actual path to the WAL file. So every time it needs to archive some WAL, Postgres will call that script and pass it the name of the file that needs to be archived. For testing purposes, I've also set the archive timeout to 60 seconds, but that just means that we're guaranteed to always get a piece of WAL to archive at least once a minute, so I can see things happening while I'm testing. I'm then going to create a WALE creds file, which is where I'm going to store the credentials. Now, in the WALE documentation, they suggest to use daemon tools to do this. I've found daemon tools to be fairly unsupported these days, and particularly on Red Hat platforms, you end up compiling it from source, and it just gets painful. But the net effect of what they're doing with daemon tools is effectively storing the credentials in a file that's kept secure, and then feeding them into the environment of the command that's doing the archiving. So here what I'm doing is just setting up some of the parameters in the creds file that are going to be used. So we give it the URL of the what's known as the Keystone authentication server. Keystone in OpenStack deals with authentication of users and service location. We give it the username to talk to Swift to and the password, the tenant name that we're going to use for this, and then the prefix of the bucket in Swift that the data is actually going to be stored in. Now, very, 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 very important is that we secure that file. Postgres needs to read it, because Postgres is going to read it when it runs the archive command. So we change the owner in the group to Postgres and give it mode 600, so no one else except for root can read it. Then create a very, very simple script. This is the script that Postgres is actually going to call. All it's going to do is source the file with the credentials in it, and then call WALE with the right command to actually push the WAL across. We make that executable. We restart Postgres so that our changes to the configuration take effect. And then just tailing the log file, you can actually see every 60 seconds virtually incomprehensible block of text like that. Does make some sense when you start to really read into it. But basically what that's telling us is that the WAL files are being archived, and when we go and look at it in Horizon, we can actually see the various different WAL files down here, each one of which has been compressed. So they're nice and tiny. Now the other thing you see, the one with the long file name, is just a flag which it uses to know what's going on. I thought there was another file in there. Yeah, it's the one above it, the one above the one with the really long name is actually a full backup. So WALE has a command line option. You can just tell it basically back up this server now, and it will just do a full base backup into Swift. And well, that's it really on WAL archiving. It's really that simple to set up. WALE has obviously other commands to restore to a point in time, restore a base backup, and so on. They're just simple command line options that are very, very easy to use. So, Chris tells me I've got 2 minutes left, which is good because I'm right at the end. Quick summary. We can deploy our standardized maintainable database servers straight from Glance in pre-configured images. We can configure database optimized compute nodes. We can configure database optimized machine flavors in Nova to target the compute nodes that we've created and configured. We can choose the instance storage based on performance and flexibility requirements versus budget. We can select the data storage based on complexity versus flexibility. We can use Neutron security groups to provide standardized security configuration outside of the instance. And we can use our virtual networks to create the logical isolated clusters of machines, whether that's for a particular application or a particular cluster of database servers, entirely up to your requirements. Finally, we can very easily deal with base backups and archiving of WAL straight to Swift using WALE. Makes it very, very easy to deal with backup management, redundancy, scalability, etc., etc. Any questions? Yes. Yes. Well, I assume so. I'll make it available to Chris anyway. Yep.
What kind of durability does Swift offer when you archive a WAL file?
So the way Swift works is it has these things called rings that it uses to determine where the storage devices are and on what servers. And you can configure in the system how many copies of each thing to have and so on. When you archive to WAL, archive the WAL into Swift, it's going to copy it onto one of those servers, and then asynchronously synchronize it to however many replicas it's configured to do.
So does that mean that when the archiver process gets a response, that the file is only in one place?
As far as I know, yes. Swift will then use rsync to actually copy it to the different devices.
So you have a short window where it's not,
Potential. Well,
where it's not replicated.
it's still on your database server as well, of course. Yeah.
But Postgres doesn't know that it may have crashed.
No. Postgres only knows when WALE tells it it's actually got the appropriate response from Swift. Any more? In that case, thank you very much.